So poem number 61 on chapter 4 homework says the motion of a ball between being thrown up is in the table. We have the time in seconds and the height. And we'd like to use technology to create a scatter plot for the data. We're going to use Desmos to do it. You just go to desmos.com/calculator to get there. And the nice thing about Desmos is I can actually just copy this data, do Control C or Command C on a Mac, and then paste it by Control V on a PC or Command C on a Mac. The nice thing is when you do that, Desmos actually redoes the window based on the data and draws the graph for you right there. If you'd like to actually get this graph and copy it, you can actually do share your graph and then export the image. What I like to do is I look at this and it looks like it goes up, then it comes back down. This does not look like it's a nice repeating one because there's no reason for the ball to come back up again. Unless it bounces, and even if it bounces, it won't actually come up exactly the same way because of physics. So it's not going to come back up. It's not going to be periodic, but it definitely has this U shape to it, which kind of tells me it's either quadratic or parabolic or parabola. So we're going to use a parabolic graph for this to see what happens and to come up with the actual appropriate model. So we're going to go into our modeling, the start of the modeling in the chapter, to see what a quadratic equation actually looks like, what that function model looks like. So at the start of the modeling section, we actually list all the different models that you might see. And there's other models you can see, but these are the ones we're going to look at in this class. And parabolic or quadratic is right here. And it says y is equal to ax squared plus bx plus c. So that's actually what my basic graph looks like. So that looks like what we're going to have. So we're going to have, that's what we're going to put in here. My input value is x1. My output value is y1. So I type a y and then a 1, it automatically makes into a subscript. If I then do a tilde, that's what tells Desmos, I want you to find the equation and not just plot something up. And then I want to type in a, my parameter a, times x squared. The square, the times is the star. The power is the caret, which is above the number 6. So x squared plus bx plus c. Oh, but I don't have x. I have x1 is my variable. So I do need to put a 1. Again, if I type a 1, it automatically makes it a subscript. And there. And now I see I get my nice plot. It looks like it matches quite nicely to my data. Everything looks pretty good. I now can see I have my parameter, my a, my b, and my c. So I can now write down what my equation is. My equation is y is equal to a, which is negative 495.7 x squared, plus my b, which is 234.4 times x, plus my c, which happens to be negative 0.36. You can make it plus a negative, or you can just make it negative 0.36. So there's my equation. There's my model that models this equation, this data. I want to determine my r squared value. Desmos gives it to me. It's 0.9998. And what that means is 99.98% of the variability in the height of the ball is explained by the model. So there's not a lot left over now. That doesn't explain why it does what it does. That's physics that would explain that. But at least it gives you an idea of how I can predict what the height is from what time it happens to be somewhere. And in fact, we can use this model to estimate the height at 0.25 seconds. So I can actually copy this model. You can either type it into your calculator, or you can copy and paste it or type it into Desmos. I don't care. I'm going to copy and paste because I'm a little lazy here. So I'm typing, did that. My x's I want to use are 0.25. And then I'm going to multiply that by 0.25. And there's what height it's going to be, 27.3. So at 0.25 seconds, the height is 27.3 centimeters. And I do go back up, just make sure it is centimeters. So that's how high above wherever I threw it, the ball is. Or the table, I guess. All right. All right, and now we want to now predict what it is. By the way, can we trust this? Well, when I look through the data, I notice that 0.25 is not actually a data point, but I do notice that 0.23 is a data point, and 0.25 is a data point, and 0.3 is a data point, 0.256. So 0.25 so falls somewhere between 0.23 and 0.266. So even though it's not one of my actual data points, I can trust it because it's following along exactly where this data is. 0.25 is right about here. It's actually following along with what the graph is. So we can trust it because it's part of the original data. Let's go ahead and do it now for 0.6 seconds. So I'm going to change these 0.25 to 6. And I get negative 38. Now you might think, well, I can't get a negative height. But we are throwing this from a table. And if it goes off the table, it could have a negative height because it could fall down below the table. So the negative isn't really what clues me into there's a problem. Really, the problem is that if I look at my times, the highest time I have is 0.46. 0.6 isn't anywhere here. I don't know what happens after 0.46. It could be that the ball hits the ground somewhere in there, in which case the height's not going to change at all. It could be lots of different things that could happen. So I can't trust it when we're beyond the data. So if we're not in the range of the original data, I can't trust that value.